All right, so we have 8.3 notes, the second day of them. So our goal today will be to graph log functions. In the other set of notes, you guys learned how to convert from exponential to logarithms. You guys also learned how to evaluate logarithms. Both of those they're very important for today's stuff. So our goal is to graph log functions. All right, and then way back when, we talked about what inverses were. And if you remember when we tried to solve for an inverse, what you would do was you were going to take the x and the y and they switch places and then resolve for y. And so you can see from the table on the left to go to the right, all that we did was switch the x and the y. The y becomes an x, the x becomes a y. So these two graphs are inverses. Okay, and then we resolve for the y. Well, in order to get the exponent by itself, you're actually going to write this instead as a logarithm. So we have log. Again, this is why I told you that it's very important that you know how to convert easily. The basis 2 of x equals y. So you can see here that this is actually y equals log base 2 of x. And so that's what we're graphing here. So the left one, you guys should already know how to have come up with this table. Over here, y equals 2 to the power of x. Plug in, let's see, we have negative 3 through 3 for your x values. When you plug in negative 3, 2 to the negative third is 1/8, 2 to the negative second is 1/4, 2 to the negative first is 1/2 to the power of 0. So you guys know where this table comes from, right? Well, again, when we move to the log function, all that happens is your x and your y switch places. We have 1/8 comma negative 3. Instead of negative 2 comma 1/4, we have 1/4 comma negative 2. Instead of negative 1 1/2, we have 1/2 negative 1. And then when we plot these, you have the inverse function of the exponent. Well, one of the things that we have talked about, so this is actually the blue function over here, y equals 2 to the power of x. Okay. This green line, though, what is this green line? Well, if it's a line, it has to be linear, so y equals, and there's no y-intercept, and the slope is 1, so y equals x. You guys might recall when we did inverses that the inverse always reflects over this line, so you'll notice these reflect over, okay? So this blue line reflects right to this red line, which is this equation over here. So this equation is log base 2 of x, okay? Or y equals, I should write, y equals log base 2 of x. Or you could write it as x equals 2 to the power of y. I don't care for right now. But this is, I wanted to show you how you get to a log function on a graph. It's just the inverse of an exponent of an exponential equation, and you guys, I'm sure, we're fine with that. So let's talk a little bit about these parent functions then. The parent function of an exponential, we talked, was just the base and then the exponent, or the growth factor and the exponent. So y equals the b to the power of x. So you don't have the a value, you don't have the h and the k, none of that stuff. It's the most simple form of an exponential. And we knew that your domain was x as an element of all real numbers. Remember those rules we talked about, those cheat sheet rules? So you guys should always know these. Your range would be y is an element. Remember, it goes from the asymptote to infinity. So on the parent function, our asymptote would be at 0. So 0 to infinity here. And then your asymptote was always that horizontal line. So that horizontal line would be at y equals 0. And if you needed a little cheat sheet or how to write those in, if you scroll back up and you look at this function here, you can see that you would keep going to the left, you would keep going to the right, which is why your domain is all real numbers. For your range, you can see that it is going to approach that 0 line and keep going up. So it goes from 0 to infinity for your range, which is where we come up with the range. The asymptote, remember, is that dashed line that it is going to be approaching. Okay, So you know that that blue is going to continue to approach that line. All right, so then let's go back down and let's talk a little bit about then what the logarithmic function is. Remember, this is the inverse, so the x and the y change. Let's actually write that in. So anywhere there was an x, now there's a y. Okay, so since your x and your y's are changing, what's going to happen, the parent of a logarithmic function is just going to be log base b of x. Okay, and then what's going to happen is the domain, which was your x values, since your x and your y's change, that's going to become your range. Okay, so now what happens, your range is going to be f of x is an element of all real numbers. All right, let me get my pointer here. So then your range, which was your y values, now these are going to become x values. So that helps you determine what your domain is going to be. All right, so your domain is now x is an element from 0 to infinity. Okay, your asymptote used to be y equals, so now it's going to be x equals. All right, we are going to practice graphing this on the next page, so don't worry about that, but I wanted you to see that you're going to be able to come up with these rules just like we did for the exponential, and I wanted you to see where they come from. All right, actually I want to go back. Okay, that b, which is your growth factor when we're talking about exponential functions, that b, remember we said that b is not allowed to be negative and it'll never be 1. Okay, so your option is between 0 and 1 or larger than 1 is what we said for b. That is the same case with logarithms. Okay, your b was your base here, it's still your base here. Okay, the base, and that is considered a base also. That does not, the rules for b does not change. So when we're talking about this, this is what this example on the left, this is what it's going to look like if your b value is between 0 and 1. Remember, it can't be 0 and it cannot be 1. Okay, so then the example on the right is what would happen if b was larger than 1. All right, so let's talk a little bit about there's 3 points. They might be a little bit hard to see. Let me see if I can point to them. There's a point here, here, and here on this graph. On this one, we have a point here, here, and here. Okay, so on this graph, what we are actually graphing is f of x is equal to log base b of x. This would be considered, actually, you know what? Let's write this as y because it's just going to be a little bit easier when we change it to, so y equals log base b of x. Okay, so b to the power of y is equal to x. All right, so when would this is your y value, okay? So this point right here, if you have b to the power of 0, that equals what? B to the power of 0 is equal to 1, okay? So that's telling you that when y is 0, x is 1. So that point right there is 1, 0. No, I'll actually leave it in green. I'll do each one a different color, so it'll be a little bit easier to see. All right, so then this point right here, okay, this point is at -1, y value, okay? So b to the power of -1 is actually going to equal 1 over b. So for the y value, and notice that we're plugging in y values because it's much easier to plug in for the exponent to figure out what x is versus what would the exponent be if this was your answer. So that's where I'm coming up with these. I'm plugging them into the y value. So on this one, our y value was -1, and the x value is 1 over b. Okay. Then for this point here, where the y value is 1. B to the first power is just going to be b. So this point is at b comma 1. Now you might notice that there is an error on my key. I just realized that with that third point, the yellow one, it should be 1 over b comma negative 1. All right, so then let's talk about when b is larger than 1. Now notice also, let me get my pointer here, that b has to be between 0 and 1, so that's why this is at b comma 1. And it looks like it might even be on the x-axis. It's not on that y-axis. It's just probably pretty close to it with that b being between 0 and 1. All right, so then let's figure out this. So this has a y value at negative 1, so negative 1. B to the power of negative 1 would be 1 over b, so that's what that is going to be. Let's do green. This point here, your y value is at 0. B to the power of 0 would be 1, so that's at 1 comma 0. Notice that point is on both of these. And then the last point, let me make that yellow. This was at a positive 1 for the y. B to the first power is going to be b. So this does look a little bit different, but essentially what you want to notice is that your y value, 1, 0, and negative 1 are all really easy to plug into, and that's how we're going to be graphing these functions. So if we turn it over to the back side of the notes, or I have no idea how your packet was copied, so maybe the next page, not really sure. All right, so what I want you to notice is that the first two examples are both examples of parent functions here. They don't have any a values out front. You're not having any translations, shifts. So we'll get down into that in a little bit. But what I want you to see is that if I wanted to write this as y equals log base 2 of x, that might be a little bit easier. This is the exact same thing as 2 to the power of y equals x. Okay, this is a little bit more user-friendly than thinking about the logarithms, because logarithms are kind of foreign to you as of right now. They're just learning a new language, right? But exponents are something that you guys have known about for quite some time, and so that might be a little bit more familiar to you. But what I want you to see is that when you have these, you can come up with multiple points, okay? And those couple points are a lot easier if you plug in to the y, okay? So 2 to the power of negative 1. 2 to the negative first power is going to be 1/2. 2 to the power of 0 is going to get you 1. And 2 to the power of 1 will be 2. And so you can come up with points. Now that means that we could graph that function because you would have 3 points. Now this right here is not an inverse of this, okay? Because the x and y, you're not switching them. They are equivalent. These are equivalent. So this is the logarithmic function that you're trying to graph right now. You just wrote it in a more familiar way. Now, if you graph these points, you're on your way of graphing a logarithm. All right? So the next example, I gave this one with a base of a fraction because I, again, want you to see this. So if I write this as y equals log base 1/8 x. Don't know why I was writing over there. And then what happens when you convert it, you're going to have the base is going to be 1/8. Your exponent is y, and that equals x. Okay, so this looks like, oh my gosh, this is crazy, right? It's the exact same thing. So you can come up with a couple of points, plug into your x. The easiest exponents to evaluate at are 1, 0, and negative 1. Those are probably the 3 easiest things to evaluate. If you take 1/8 to the negative first power, all you're doing is you are flipping the fraction, okay? So what you will get is 8. Take anything to the 0 power, you get 1. Take anything to the first power, you get exactly what you had. So there you have 3 points. Okay, now let's talk about the domain, range, and asymptote for these. Okay, The domain, okay? Let's see. Where were you able to plug in your numbers? You were able to plug them into y. That was the exponent, right? So your y values are what, right? These y values are where you plugged in. So your y values are your exponent. That is your range. So your range, remember, is now all real numbers, okay? Remember, the roles are flipped. Your domain, if you look at this, you have 1/2, 1, and 2. Notice if you were to make these larger, what would happen would be these numbers would get larger, right? 1, 2, 3, 4. 2 to those powers get really big for your x values, okay? If you went more negative, then you're going to have 1/2, 1/4, 1/8, 1/16. Those numbers are going to get really, 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 really tiny. They will approach 0, but they will never reach it. So your domain is going to be x as an element from 0 to infinity. And yes, if you want to write this x is greater than 0, that would be fine too. Okay? Your asymptote, well, which one has a limit to it? Well, your domain, which are your x values, is where your limit is. So your asymptote is going to be at x. X equals 0 is where they approach but never reach. So there's your asymptote. And actually, those are going to be the exact same for both of these functions. Okay? So this goes on this side and it goes on that side because these are both parent functions. So those are just, that's the rule. All right, so if we go down, let's talk about these transformations. If you have x minus h, this goes right. If you have x plus h, it goes left. Okay, there's your horizontal. So inside with the x, inside those parentheses. If you have plus k, it's going to go up. If you have minus k, it's going to go down. These are no different than what you are used to. All right. Your a value, all right, that is if your a value is larger than 1. It's a vertical stretch. If your a value is between 0 and 1, again, it will not be 0, it will not be 1, then that is a vertical shrink or compression. All right. If a is negative, now notice those are the values of a because I didn't talk about if it was positive or negative. If a is a negative value, then it's going to reflect across the x-axis. Okay, so it's going to flip it. All right, let's now move on. Let's talk about actually doing this example that is no longer just the parent function. On these ones, you are going to want to think of the parent function, which remember the parent function is just log base 3, there's your base, of x. You're going to ignore the horizontal asymptote, the horizontal shift, you're going to ignore the vertical shift, and you're going to ignore that a value. Okay, so our parent function, which we're going to write over here, would be log base 3 of x. All right, let's go ahead and we'll write this in a exponential way because it's a little bit easier to deal with. So 3 to the power of y equals x is what we have. And then what I'm going to do is I'm going to come up with a table, okay, x and y. Remember, if you plugged in something for your x like 4, 3 to what power gets you 4? That sounds miserable. I wouldn't do that. I would plug in -1, 0, and 1 on the y because those are the easiest ones. If you want to go to -3 and +3 like we were on the exponentials, that's fine too. You're just going to find more points. All right, so 3 to the -1st power is 1/3. 3 to the power of 0 is 1. And 3 to the 1st power is 3. Next, we go to the sibling function, which is when you take into consideration that a value. So what's our a value here? Let's take a look. Our a value is 2. So now we're going to have y equals 2 times log base 3 of x. And so what you're going to do to get there is you're going to multiply y by 2. That's your multiplier. So let's come up with our table here. Nothing happened to the x values. So our x values stayed the 1/3, 1, and 3. Nothing happened there. But your y values are all multiplying by 2. So -2, 0, and +2. All right, then what we're going to do is we're going to take in consideration that shift. So this goes right 2 up 1. So that's how you get to the baby function. Right 2, because of that x minus h means right. Add the 1 at the end, that's up. So right 2 up 1. Okay, right 2 up 1. That means that that vector is 2, 1. So you're going to add 2 to the x values, and you are going to add 1 to the y values. So let's see, that's 2 1/3. 3, 5. We have -1, 1, and 3 there. So now you have your 3 points that we can go ahead and plot those. So let's see. You can also think of your domain, range, and asymptote for each of these. That would probably be a little bit easier, like what we did with the exponentials, in order to figure out what your domain, range, and asymptote is for the final, because we will need that. So you have your domain, range, and asymptote here. All right, let's go ahead and do this graph. And like I said, you can do more points on here if you want to. I'm just getting it started for you guys. All right, so then the 3 points we found for that baby function, 2 1/3, -1. So 2 1/2, 2 1/3, -1 would be right about there. And the next one was, 3 1. So 3 1. And then the last point was 5 3. All right, so let's now talk about the domain, range, and asymptote. Now, what was all real numbers? That was, which we talked about it up here. So let's see. Your range was all real numbers. So that one's obvious. That's not going to change, okay? So y is an element of all real numbers, or f of x, okay? That means it's going to go forever down and forever up. So you can kind of see that here. This goes forever up, and this is going to go forever down, okay? Now, if we go back, your x went from 0 to infinity for a parent function. But what happened with the x functions? If your parent function went from 0 to infinity for the x, right? What did you go from here to here? You didn't do anything to it, so it's still going from 0 to infinity. What did you do to the x values, though, when you got to the baby function? You added 2 to it. So now you're not going from 0 to infinity, but instead from 2 to infinity. So that's what your domain is going to be, okay? So your domain is going to be x is an element from 2 to infinity, or you can say x is greater than 2. Either way, it doesn't matter. And then that 2 is your asymptote. So you have a vertical line, right, at x equals 2. And we want to make sure that we always graph that asymptote also as a dashed line, so you can see that you're approaching it. Now, let's try to figure out where that 2 comes from. That 2 was the h value. You can see that, right? So there is actually rules for this that we can write down. Your domain, using that function right there with everything, your domain is always going to be from the asymptote, okay? That asymptote comes from that horizontal shift, okay? So right here. And notice that it does show up opposite that it does in your equation, because that h value shows up as opposite because it is read as negative h there. So your domain goes from h to infinity. So x is an element from h to infinity, or you can say is greater than h. Doesn't matter to me. Your range, that one, nothing changed. Y is an element of all real numbers. And then your asymptote is going to be affected because your parent function, it was x equals 0. It's an x, so that's affected also by your horizontal shift. So it's going to be at x equals h. Again, that domain and the asymptote are going to have those same numbers in both of those things. Just like it did here. They both have the 2 in it. Okay. So hopefully that helps for you guys. If you guys have any questions, let me know. Other than that, good luck on the graphing part. Make sure you're checking your answers also. And like I said, if you have questions, let me know. Thanks.